Hello. Today we will discuss about vector, field, Maxwell's equation, and from Maxwell's equation we will try to derive the electromagnetic wave equation. So let's start the idea of field first. The field is a function, a mathematical expression which assigns the value for every point in space and time. So you can think about any function. Say I am representing any function as phi. Now the position in three-dimensional space I am representing it by r and time t. So this can be considered as field, a mathematical expressed by this function. Now this values of this function may be some numerical value, simple numbers, then they will be simply representing the scalar field. But if they are vector, they will be considered as a vector field. So there are a number of examples of scalar field like heat, water flow. They are basically the scalar quantities. Whereas the vector fields, the simplest ideas of vector fields are electric field, magnetic field, gravitational field, all are under the belt of vector field. So let's see what is the basic idea about vector field. Vector field is a set of vector assigned to each point in space. So it's a vector assigned. So one can think about a region where you have certain field. Now this field is a vector. So if you think about any point over there, so there will be a vector value. If it comes somewhere here, and some other points on this region. These are the vectors. These assigned vectors in a certain space region. So we are considering a defined space region, something like this. This will be considered as a vector. Now one of the example it is shown over there. This is the wind flow on the Earth's surface. So how this will be designated? This is given by this one. Now the examples we have already considered, the magnetic field, electric field, the gravitational pull, all are under this vector field. Now if you know about field, so then it helps us to solve any continuous system by using some mathematical models. Now, when you have a field, certain region, this may be in a geometrical shape, this may be in a non-geometrical shape. Now, we can handle the problem mathematically. So, how we can do these things? Now, if you have a field, then by using certain parameters, certain operations, one can solve the problems. One can get detailed information about the field. So, what are those operators? What are those operations we can use to get the details idea? There are three important operators are there. They are known as the vector operators. They are known as gradient, divergence, and curl. These operators will be operated over vector field. So what is gradient? In simple word, so the gradient will be operated over vector. This will give you a scalar field. Sorry, when this is operated over a scalar field, this will give you a vector field. So if you have some water flow, so mathematically it's not a vector quantity, but if you are operating it by gradient, so you can represent, mathematically you can represent this water flow field as vector field. So how are you going to do these things? So gradient of a scalar field at any point represents the maximum rate of change of scalar field for the position. And it's always directed along the normal to the field surface at that point. So if you are considering any region, say this is a scalar field region. Now one can just imagine that this is a coordinate system. So I'm considering a linear coordinate system where you have the component x, y, and z. So this is x, this is y, and this is z. So what we're going to check? We're going to check what is the maximum rate of change. So how to find it maximum rate of change? So one can use the concept of differentiation. Now, the vector phi, so it is represented by phi. So one can check the variation of phi along x direction. So how to represent it? This simply will be written as d phi d of x. As phi is function of x, y and z, so we need to consider the partial differentiation. Same way one can write it the variation along y, d phi dy and d phi dz. So this is the idea about the gradient. Now what will be the direction? What will be the direction? This will be normal to the field surface. You need to consider the normal to the. Now the first and foremost thing what we have mentioned about gradient is this will be operated over a scalar field and this will give you a vector. So now if you have initially if you have a phi scalar quantity, now you are differentiating with respect to position. Plus I'm just writing in that form y d phi dz. There will be a plus sign. So phi is a scalar quantity, but as we have checked it for different directions, so this can be represented as a vector thing. So the direction, this will be normal to this, so it can be represented as I cap, this can be j cap and this can be k cap. So one can consider this is as v of x, this can be considered as v of y and this can be considered as v of z, and the directions are I cap, j cap and k cap. Obviously when you are able to represent a scalar quantity in that form, then they will be considered as a vector. Not physically but mathematically they will be considered as a vector. Now if you are able to convert the thing in form of a vector, now we can handle the problem much easier way. Mathematically we can deal the problem easily. Now this is the expression by which one can solve a gradient problem in a Cartesian coordinate system, in a linear three-dimensional coordinate system. So this is the notation and this is the operation mode. Now comes the next part. Now you have the vector field. Now you don't need to bother about the scalar field. Now you have a vector field. So all the fields available we can easily convert into vector field. Now we can deal with the vector field. Now the vector field, now the divergence operator, our next operator is known as the divergence operator. The divergence of a vector field, obviously you have converted the field into vector field, any of the field into vector field. So the divergence of a vector field measures the tendency of the field to collect or disperse at a point. Now again you can just consider a point on the surface. So this is the vector field. Now we are considering any point over this. Now we need to measure whether that field is collected over there or dispersed over there. Now the simple way one can think about whether there is a outward flow, disperse, or whether there is a inward flow, the collection. So if you think about a field, some flow of water, some heat field, you can think about electric field, you can think about magnetic field. Now you need to study whether the field is acting as a collector or a disperse. So if you are operating by divergence on the vector field, you will get some idea about it. So the operation is something like this. So when you are operating over this, so again you are just checking it, the directional derivative, d dx, d dy, d dz. Now if the vector field, divergence of a vector field is positive, then we will say that it acts as a source. That means the field, it represents the field in dispersed mode, if in a outward flow mode. And if this is negative, if the divergence value is negative, then this is act as a collector. It is act as a sink, one can think. If this is positive, this is act as a source. If this is negative, this will act as a sink collector. But there is another possibility. The possibility is the divergence of the vector field is equal to 0. That means nothing is going out, nothing is going in. The field is in a closed system. So then the divergence of this vector field will be equal to 0, and this will be considered as a solenoidal vector field. So one can just simply write the divergence of the vector field. If this is equal to 0, then this is solenoidal. If it is greater than 0, so this will be considered as source. Greater than 0 means positive. If this is less than 0, then this will be considered as a sink collector. Now comes the next part. It's known as the curl. So curl means this will again be operated over a vector field. Now it will go to check the tendency of this field to square, to curl in the system. So one can just think about if you have whether you have a curl in the system or not, whether you have some rotational movement or not. How are you going to find that? This will be simply calculated mathematically by using the basic concept of determinant. So one can give ijk, it's a direction. Then what you have to do? You have to give del del x, del del y, del del z. And the vector, what we are talking about, say fx, fy and fz. So what we have done? Initially you have a scalar field. We have converted into vector field. Now vector field having component fx, fy and fz. Now we need to check whether the system, is there any curl in the system or not, whether there is a rotational motion or not. This will be calculated by curl. If the curl value, the overall curl value is equal to 0, then obviously there is no rotation. There will be no squeal of the field. But if this is non-zero, then obviously there will be curl in the system. If the vector field is 0 after operation by curl, then this will be considered as a conserved field or irrotational field. But if this is not equal to 0, then if it is not equal to 0, then this will be considered as a rotational field. It's a rotational field or a non-conserved field in the system. So in simple way one can think about, you have some field region. Now whether the field is moving or not, whether the fields are moving in a different direction or not, this can be calculated by grad, divergence and curl by using these three operators. And these operators are basically mathematical operation of differentiation. Now the most important part is when you talk about differentiation, you are talking about the elementary part. You are slicing the whole system into smallest ever part. And theoretically, the del del x or delta del x, this must be tends to 0. This will be very, very small. Now the next part is the system, whether if it is a one-dimensional system, it may be a two-dimensional system, or it may be a three-dimensional system. You can think about dx in one dimension, dx dy in two dimension, dx dy d3 in three dimension. So all the elementary components must be very, very less. Now to get idea about the whole system, you need to integrate over this elementary part. If this is one dimension, there will be 1D integration. If this is two dimension, there will be two integral. And if this is three, there will be three integration. So for one dimension, this is known as line integral. For two dimension, this will be known as surface integral. And for three dimension, this is known as volume integral. Line integral, surface integral, and volume integral, depending on the shape of the system, shape of considered system. Now here, we need to think about three coordinate systems, three important coordinate systems. So before this coordinate system, let me just talk about this integral part. So you have the elementary dx, dy and dz thing. Now one can refer one dimension, one can refer two dimension, and one can refer three dimension depending on the system, as I have just mentioned. Now there are two important theorems are there, two important statements are there, which helps us simplify our mathematical problems. Now here the first one is known as the divergence theorem. So what this divergence theorem says? The divergence theorem says, or it gives us a relation between surface integral with volume integral. So what is surface integral? You have a two-dimensional system. You have variation of x and y, or y and z, which axis you are talking about. Now what will be the relation between two-dimensional variation with a three-dimensional system? A three-dimensional system, just to think about. So this statement simply says that if you have a surface integral, this will be equivalent to the volume integral, and the volume integral will be in the form of divergence of the field. This will be divergence of the field. So the divergence theorem, that's why it is known as the divergence theorem. The divergence theorem states that the surface integral of the normal component of a vector point of function f over the closed surface is equal to the volume integral of the divergence of function taken over the volume V enclosed by the surface. Okay, so divergence theorem gives us the relation between two-dimensional integral with three-dimensional integral. Then comes the next one. This is known as the Stokes theorem. And the Stokes theorem, so you have a relation with one dimension with two dimensions. What is said? The Stokes theorem states that the surface integral, that means two-dimensional integral, of a curve of a function over a surface bounded by a closed surface is equal to the line integral of a particular vector function around the surface. Now you can just think about a surface. Now you're going to trace over this thing. Take me just different color. Okay, so you are moving over this thing. So the closed loop line integral, okay, this must be equal to surface integral, but this should be in a curve form. So Stokes theorem, sometimes also known as the curve theorem. Now you have the operators, the elementary form of a continuous system, and then integrate over this thing to get back to the continuous system. So one can just think about any field. In a mathematical form, we are slicing this into elementary form, and then we are adding by using the concept of integration. Now when you have this thing, then we need to use the concept of a coordinate system. So for a non-geometrical system, always you cannot use a linear coordinate system or Cartesian coordinate system. So we need to use some other type of coordinate system, which is just a modified form of the Cartesian coordinate system. Now here we need to talk about different coordinate systems. There are two types of coordinates basically. One is linear, another is polar. So linear is the rectangular or the Cartesian coordinate system, and the polar, the modified form of polar, they are known as cylindrical coordinate system and spherical coordinate system. So to discuss about linear and this polar coordinate system, one can take a simple axis. So let me just discuss it for 2 dimension, then we can extend it for 3 dimension. So normally we used to consider this is as x-axis and this is as y-axis. So it's a linear coordinate. So any point on this surface can be represented by some values of x and some values of y. So this will be considered as x and y. Now this object can move on this surface. Okay, so just imagine you have this point and this point is moving like this. So one can just think about a point here, and after some time you have. So we need to think about this distance. So initial point was this. So distance is fixed. This r and this r is fixed. Now from this point, after some time it moves from this point to this point. Now we can get angle theta. Now this point or any of the point on this path can be represented by r and theta. So r theta, this is the representation of polar coordinate system. So in 2 dimensions, the polar coordinate system is represented by r and theta. Whereas in 3 dimension, so if you extend the third coordinate, over there, so this will give us the idea about cylindrical and spherical coordinate system. So one can think about a circle, and the circle can be represented by r and theta. Then let me just extend it for cylindrical and spherical coordinate system. Now to do this thing, so let me just focus on this simple picture. The first one is Cartesian or rectangular coordinate system, and you are considering this point and where this is the origin. So you need to have some x, some y and some z along this direction. This gives you x, y and z in the system. Whereas in cylindrical coordinate system, the variation is given by r and theta. I've just mentioned about polar coordinate system, and this is represented at r and theta. Obviously one can think about this particular point is moving. Just consider this point now, not consider the third axis. So it is moving like this. So now here this distance is r. It's a fixed distance. It may vary. It's a fixed distance. The position is represented by r and the angle theta. Now if you just consider that you have a cylindrical surface and the object is moving over this surface. Now how to represent it? Obviously that r and theta is varying. We've just mentioned this thing, r and theta is varying. Along with this thing, the height is also varying. Initially height was somewhere here. Now after some time the height becomes like this. So here in the cylindrical coordinate system, height also plays a very, very important role. And the coordinates are represented as r, theta and the height part. And the height we used to represent it by z. So it's a mixture of Cartesian coordinate system and polar coordinate system. So the height of the cylinder is not changing. Now comes the last one. So in this case also r and theta plays a very, very important role. So you can think about the sphere. R and theta value is same. But the only difference between the cylindrical coordinate system and spherical coordinate system is that now here you have a linear axis. The height is represented by a linear axis. Whereas in case of spherical coordinate system, this height is changing. This height is changing along this curve. So this side, the third axis, now this will be represented by another angle with respect to z. Okay. So in case of spherical coordinate systems, the coordinates are in r, theta and phi. Some cases instead of r, they used to represent it by rho, but the concept of r and rho is similar. Here also sometimes they used to represent it by r, theta and z. Okay, so you have x, y and z axis. This can be represented by r, theta and the height z, and here r, theta and the angle. Actually this is changing, this point is changing and it is making an angle. One can think about this point is changing along this point. So the angle phi is changing. So if you have these three coordinate points, x, y, z, r, theta, z and r, theta, phi. So you can represent your position on either rectangular or our spherical or cylindrical coordinate system. Now these are basically basic mathematical tools which will help us to explain the vector field, the famous electric and magnetic vector fields. Now the electric and magnetic vector field, they are combined by famous Maxwell's equation. Now here I have just considered all the equation, all the four equations in form of a differential equation, in form of an integral equation. Let me just explain one by one. So the first equation is known as the Gauss equation. The Gauss's law. The Gauss's law is the basic law which explains the electric flux coming out from a closed surface is equal to the total charge enclosed by the closed surface. So one can just think about a surface, a charged surface, and now we need to think about the flux. What is the meaning of flux? A small area. So this type of surface is basically covering the whole surface. So the idea is, get the idea about the flux and integrate over this. This will give you the whole surface. Okay. So the Gauss law says that the total flux, this is proportional to, it is equal to the total charge enclosed by the closed surface. Now this is given as the integral form. Obviously we are talking about line integral. So integral over electric field, this is equal to total charge divided by epsilon 0. Epsilon 0 is the mathematical expression for the lines of forces. Now, what is charge? Charge can be represented by the charge density. So what is the meaning of density? Charge density, normally density means mass divided by volume. Okay. Now here we are talking about charge. So what is charge? Charge divided by volume. And the systems are continuous systems. So now we will be representing it in terms of integration. So this is dV integrating over this. So the total charge is integration over rho dV. Now what you have here? So in the left hand side you have a surface integral, two-dimensional integral, 2D integral. But what does charge gives us? Charge gives us a volume integral. This is 3. So now you have 2 and 3. So we can convert the thing into either in 3-dimension integral form or in 2-dimensional integral form. So let me just convert this 2-dimensional integral form into 3-dimensional integral form. So what you can do? You can use the divergence theorem for this. So how to convert this 2-dimension? This will be replaced by the divergence of electric field. Now come to this point. This gives us this one. The 2D integral now is converted into 3D integral, the volume integral. Now left hand side and right hand side both are of volume integral. If they are equal, then obviously one can write this is the relation. So it says the divergence of the electrical field, this is equal to rho charge density divided by epsilon 0. A simple arrangement. So you can just take epsilon 0. This is given by capital D. So capital D, sometimes it's known as, this is known as electric displacement vector, or sometimes it's called the displacement vector field. So what it says? So here it gives us an idea about the divergence of electric field. So when you're talking about divergence of any field, so we are talking about either greater than 0, less than 0 and equal to 0. So in this case, electric field, divergence of electric field greater than 0, that means you have the positive charges. So if you have a positive charge, lines of forces are coming out from this. This is the expression of divergence electric field is equal to 0. Then the second one is divergence of electric field is less than 0. That means you have a negative charge and this is moving in. The lines of forces are moving in. And there are a number of possibilities for electric field. Divergence of electric field is equal to 0. Then this may be combination of positive charge and negative charge, so no lines of forces are moving out. Or it may happen there is no charge. So the two possibilities are there. So this is the Gauss statement. Then comes the case of the magnetic field. Same Gaussian law for magnetic field. So it is observed that for magnetic field, the single magnetic pole is not available. So one can just think in this case that the flux, again one can just think about any region where you have the magnetic field. Now one can think about a small area. So how many number of lines of forces are moving out? This gives us the idea about flux in the system. Okay, so integrate over this thing, so you will get the total magnetic field. The Gaussian law for magnetic field says the flux is equal to 0. Then again you have a surface integral. It may be converted into volume integral. So one can write the divergence of magnetic field is equal to 0. So this is a very, very significant relation. When divergence is equal to 0, that means you have one possibility that no lines of forces are coming out from this. No lines of forces are coming out from this. And it is happening every time for magnetic field. And it is only because of the North Pole and South Pole. The magnetic poles, they are always in a combined form. Lines of forces starts from North Pole and moves to South Pole. So if you have a field region, so all the lines of forces are in a closed system. Nothing is coming out from this. So in that sense, the divergence of magnetic field, this is equal to 0. So the first two laws are the Gaussian laws. Then comes the case of Faraday's law. It is basically the extension of Lenz's law. So what he says, the line integral of electric field over a closed contour, a closed loop you can think about, is equal to the negative of the time rate of change of total magnetic flux. So this is the expression, a simple diagram. So if you have a magnet and it moves to and fro, so as you are moving it to and fro, due to the induction, the flux area is changing with respect to time. So for the continuous system, in the integral form, one can write the expression like this, in the integral form of this. Electric field in one dimension, this is equal to flux, time dependent flux. It is changing with time, so flux dependent now. And you have a negative. As Lenz's law, it mentioned this thing, it will experience a force, it experience a opposite force. So when you try to move in this direction, it will experience a force from this direction. Now when you think about the flux region, you are really talking about a two-dimensional integral. Okay? So now in left hand side you have 1D integration and in right hand side you have 2D integration. So now what we can do? We can have a relation between these two. So what we are going to do? We are going to use the Stokes theorem. So what is Stokes theorem says? This will convert the 1D integral into 2D integral. How are we going to do these things? By using the card. So this will be converted into 2D integral, and obviously this is the right hand side is in a 2D integral. So one can simply write the curl of electric field is equal to minus dB dt. This is the famous Faraday's law. What it says, the time dependent magnetic field will give you the space variable electric field, or the reverse is also applicable. Now the last one, the Maxwell last equation is derived from Ampere's equation. So what it says, again this is giving you the integral, line integral of a magnetic field over a closed loop. So there are two types of current one can think about. One current, this is sometimes known as the conventional current. Current due to the flow of electrons, flow of charges. And there is another possibility that magnetic field, line integral of magnetic field will be produced due to time dependent electric field flux. And what is this thing? Time dependent electric field flux. What it says? That in case of a wire, a good conducting wire, current is passing. So here electrons are moving. Electrons are moving. Free electrons are moving. Okay? So in this case, the current gives us the magnetic field. And there is another possibility that you have a dielectric material where you have the dipoles over there. When you apply electric field, the dipole will change its orientation. When you apply electric field, one side will be positively charged, another will be negatively charged. So the negative part of dipole will be attracted towards the positive side, and the positive part will be attracted towards negative. If it is connecting with the alternative current, then the polarity of the sides are changing. So the polarity of the dipole is also changing. So the dipole will try to orient themselves. They are changing their direction. So due to this, there will be some transfer of energy, transfer of electric field. This also gives you magnetic field or the current, and the corresponding magnetic field can be generated. So the first one is known as the Ampere's law, and the second one is known as the Maxwell law of induction. So what Maxwell did, Maxwell just combined these two equations to write the modified Ampere's law. So what is there? So line integral is equal to current due to conventional current and due to dielectric current, which is known as the displacement current. Now again, left hand side is a line integral thing, and right hand side you have flux. That's when you have the surface integral, and you have current, means you have a current density. So what is current density? You can think about the charges, they are moving. So one can think about a unit cross-sectional area. So how many charges are passing through this? This gives us current density J. It's also a vector quantity. So this is given by current per unit cross-sectional area. So this can be represented at 2D integral. This is also can be represented at 2D integral. Now in the left hand side you have a 1D integral. Now what we can do? We can just convert 1D integral into 2D integral. How are we going to do? By using the Stokes theorem. Just let me just check it. So the left hand side you have a curl of surface integral, and right hand side you have the both surface integrals or 2D integrals. So one can simply write curl of magnetic field is equal to mu 0 epsilon 0 d dt plus mu 0 j. So what is j? J is the current density. So this part is because of conventional current or due to flow of charges, electron charges, and this part is because of displacement current because of the dipoles, the orientation of dipoles. So these are the famous Maxwell's equations. As a combined form, they are the Maxwell's equation. The Gaussian law, the two Gaussian laws, okay, the first one and third one, and then you have the Faraday's law, and the last one you have the Ampere's law. Now when you have electric field and magnetic field, so the most important part of the Maxwell's equation is this: he was able to combine the electric field and magnetic field in the 4 equations. So in case of first equation, Maxwell's first equation or the Gaussian equation, what it says, it gives the idea about electric field. Okay, it may be positive, divergence of electric field may be positive, negative, or equal to 0. But the most important part is the Gaussian magnetic field relation. What it says, the divergence of magnetic field is always be equal to 0. So the lines of forces are in a closed form. So this is the basic difference between electric field and magnetic field. Then comes the next part, the Faraday's law and Ampere's law. Okay. Now when you have the 4 equations, integral form and in a differential form, let me just operate over these equations and try to get something different from it. When Maxwell was working with this thing, what he did, he has taken the Faraday's law, and what they did, he just curled both sides of this equation. So left hand side you already have curl, and we will going to operate it by curl again, and right hand side you have a curl of B. So just remember, curl of B is already solved for us. So here you have the curl of B. So this equation will be simply replaced over there, and when you have curl of curl, you have this expression. Now to simplify our problem, we are going to solve it for free space. Now what is the meaning of free space? Free space means there is no charges available. So if the system does not contain any charges, then one can simply consider this is equal to 0. If there is no charge, so there will be no flow of charges, no current will be there, obviously current density is equal to 0. Okay. So the equation in free space is simply up to this point. So the divergence of, curl of magnetic field is equal to mu 0 epsilon 0 dE dt. Okay. Now when you have curl of this thing, it is divergence of electric field. In free space again there is no charge, so divergence of electric field is equal to 0. So you have this part, so this part is equal to 0, and already you don't have the current density, so your curl of magnetic field can be replaced mu 0. And E, so this particular part here, just look at this equation. So here epsilon 0 E, this is represented as D. This is represented as D. So when you just replace this one, you have minus of del square E. This is equal to minus del T mu 0 d del T del D del T. So just use your mathematical concept. So what you will get? So you will get an expression something like this. So what you have? In right hand side you have a time dependent electric field variation. Second order, obviously, the time dependent electric field variation. And what is this del square? Del square sometimes known as the Laplacian, or in simple words, in Cartesian coordinate system one can write this thing as d2x d2 dx square, d2 dy square, and obviously for d2 dz square. Actually, when Maxwell was able to get this expression for free space, very, very simplified form, he just compared this equation, this particular statement, with this expression. Actually, when the expression is in this form, they are basically represent a wave equation. Left hand side you have a space variation, second order space variation. This is equal to second order time variation. When you have this thing, so this part is represented as the velocity. So actually this is 1 by c. So one can write that d2, let me just write in this form, del square, say some y, del square y, this is equal to 1 by v square dy dt, where y is function of x position and time. It may be r in 3 dimension. So when you have this thing, one can easily calculate what will be the velocity. This is the expression of velocity in free space. And when you was try to calculate this thing, it comes 3 into 10 to the power 8 meters per second. So at that point you are able, here he is very close to certain conclusion. So now this is the equation for electric field. Now the same thing can be solved for the magnetic field. This is an electric field equation in free space for electric field, E vector. Now this can be represented for the magnetic field. Okay. So now we are going to operate it for the second term. Okay. Now again take the curl both sides. Now you know divergence, actually B is equal to mu 0 H. This is also representation of magnetic field. This is mu 0 H. Now we know divergence of magnetic field is equal to 0. Divergence of B is equal to 0. So obviously divergence of H will also be equal to 0, as mu 0 is a constant quantity. So this factor is 0. Okay. So in the left hand side you have the minus del square H. And the right hand side you have minus second order of magnetic field variation. So the B can be written as mu 0 H. So again you can have a second order magnetic field variation is equal to the second order time variation. Again you have the expression like this, and you will be able to calculate what is the velocity of the system. So it is observed that electric field and magnetic field vector and magnetic field vector, both are giving us a wave-like system, and their velocities are equal to the light velocity. From that, Maxwell was able to conclude that the light is a EM wave when you have a fluctuation of electric field and magnetic field. And from number of experiments, we know Oersted experiment, Faraday's experiment, we know this thing, they will be in a perpendicular direction. The magnetic field and the electric field, they will be in a perpendicular direction to each other. So one is electric field, another is magnetic field, both are vector quantity. So the energy, light wave or EM wave energy, will follow the resultant direction of these two vector components. So this is the basic idea about the light waves. Now what we have discussed, we will discuss simply in terms of Cartesian coordinate system, although we have some idea about the cylindrical and spherical coordinate system. But the operators, how are we going to operate this thing, how are we going to do these things in case of different coordinate systems? Now this simply be given us by this particular step. Now this is a very, very generalized form of gradient, divergence and curl. They are written in a generalized form. So in this generalized form, here we can write it for Cartesian coordinate system, cylindrical polar coordinate system and for spherical coordinate system. Just look at this. The axes are x, y and z, r, theta and z, r, theta and phi. So what will be the relation between x, y and z? This is given here. And some of the parameters, h parameters are given. For Cartesian coordinate system, this is 1. For cylindrical coordinate system is 1, r and 1. And for spherical, this is 1, r and r sine theta. And this is the general expressions for the operators. So gradient, divergence and curl. If you want to write it for Cartesian coordinate system, all h values will be equal to 1. But if you write it for the cylindrical coordinate system, our h2 value will be equal to r. Okay. And if you write it for the spherical coordinate system, so our h1 will be 1, h2 will be r, and h3 will be r sine theta. You can just put it over there and you can get the simplified form of the operators for different coordinate system. If it is applicable for gradient, this will be also applicable for divergence and also it for. So in a very simple form, make it, just compile all the things. So we have started with the idea about field, the concept of scalar field and vector field, the basic definition of vector field with certain examples, then the operators, gradient. What gradient will do? It will convert a scalar field into a vector field. If this is greater than 0, then this will act as a source. If this is less than 0, this will act as a sink. And if this is equal to 0, then this will be a solenoidal vector field. So the divergence. If this is for curl, so curl, there are two possibilities, either equal to 0 or not equal to 0. If it is not equal to 0, then this will be considered as a curl in the system. And if this is equal to 0, this will be considered as a irrotational or conservative field. And obviously not equal to 0, the non-conservative field or a rotational field. So we have three operators: gradient, divergence and curl operators. Then comes the next part. Three different coordinate systems: Cartesian, cylindrical and spherical. These are the simple diagram, and these are the relation by which one can write different coordinate systems, the operators in different coordinate systems. Then there is important relation between the elementary part, the differential form, with the integral form. So there will be relation between two-dimensional integral with three-dimensional, one-dimensional integral with two-dimensional integral by divergence theorem, or sometimes it's called the Gaussian theorem, and by Stokes theorem. It's known as the curl theorem. Now Maxwell's equation, electric field for Gaussian and for magnetic field Gaussian, these are there. So divergence of electric field equal to rho by epsilon 0. Rho may be positive, negative or equal to 0. Three possibilities are there. But for Gaussian law for the magnetic, the divergence will always be equal to 0. So this explains that there will be no monopole exists. There is no monopole, no magnetic monopoles will be available there. Then the Faraday's law, this gives you the final statement: curl of electric field is equal to time dependent magnetic field. Ampere's law, here there will be Ampere's law and correction of Ampere's law by Maxwell. What there will be? There will be for the conventional current, for the flow of electrons, and for the dipoles, for the dielectric material. So if your system having capacitor, then this equation is important. So the total expression for the corrected Ampere's law. Then we are trying to derive electromagnetic wave for free space. So finally you have got an expression: space variation, second order space variation of electric field and magnetic field in one side, and second order time variation in other side. And from that one can conclude this is in the form of a wave equation, and also one can calculate what is the velocity of the thing. From this derivation, Maxwell was able to conclude that a EM wave or a light wave, if there will be fluctuation of electric field and magnetic field in the perpendicular direction, and the velocity of light will be equal to c, 3 × 10⁸ meter per second. Thank you for your attention.